Okay, welcome to the OTIS AIME stream. So yeah, this is just for I'm just gonna like show how you do all the problems cleanly. So like for I think most of the problems on this AIME, like there was usually a solution that was like pretty low effort execution. Not all of them, but a lot of them have like a lot shorter solutions than people are expecting. So I'm hoping this won't take too long. I'll try to provide like kind of useful commentary or like backstories or whatever. But also at this point, by the time you're watching this, the full report should also be on the website, which also contains a lot of information. I probably spent way too much time editing all the solutions to make them really, really clean. Um, so yeah, you can also read that. But I know some of you like video content, so here we go. All right, let's do this. Uh, Problem one: you want to find the number of solutions for 0x less than or equal to 100 such that x squared is equal to floor x times ceiling x. So the TLDR is like, okay, there's going to be two cases, all right? If x is an integer, always okay. So x equals 1 through 100 are all fine. And if x is not an integer, meaning x is between x and x plus 1, then, sorry, n plus 1, then this thing, the equation actually literally just says x squared equals nn plus 1. So x is root nn plus 1. And so in other words, the other class of solutions are the things that go from root 2, root 6, all the way up until root 99 times 100. So there's 100 things here, there's 99 things here, and then you total those up and you get 199. Yeah. Okay, great. Problem two. So I have maybe it's faster if I just. I think it's faster if I show you the picture from the solutions pack instead of just trying to redraw it here. So you had a regular hexagon bodis, and then the diagonals met at E or something, and you wanted to find the purple. What fraction of the thing is this purple region here? So you could brute force it if you wanted to. That's fine. But the other thing you can do is if you take this purple triangle here and you move it here, then like this entire bottom thing is a half, and this triangle here is 1/6. One way you can, if you can't see right away that it's 1/6, I think one clean way that you can see it is if I do this. You get 6 copies of the triangle, and this is one of them. So 1/2 plus 1/6 is equal to 2/3, and 2 plus 3 is 5. Yeah, in hindsight, yeah, I think when I looked at the statistics, it turned out this problem was easier than problem one. So yeah, probably I should have switched these two, but yeah. Okay, going on. Problem three. So you have this panda that's just eating a bunch of bamboo. You know, I think this will work better if I just use one screen and not have the Zathura open. Sorry, let me change the setup slightly. We're just gonna hide the statements and then copy paste the statements as they come up. So. Yeah, I think this will work better. This is better screen space management. Shoot. No! Undo. Undo. Where's the undo button? There. Okay, cool. Okay, here's problem three. So if you know linearity of expectation, then this problem will die right away. Like if you know linearity of expectation, then you don't have to think about the problem. So let me write it out just for educational reasons, so the people who haven't seen this theorem before know what's going on. But if you have done EV comp in OTIS, you better get this problem right. Unless you computed the number of expected value on Friday instead of the total expected value, which I guess happens sometimes. But okay, here, imagine this tree, all right? where I wrote out the values just so you can see them. Obviously, during the contest, you're not actually supposed to like write out every value on the tree, but this is just for concreteness. So essentially, there's like, because there's 4 days, there's 16 things that can happen, and I've drawn them on this tree. And if you imagine what happens in this tree, like one possibility is you always go up by one. So it's like, well, 14 plus 15 plus 16 plus 17 plus 18. And then on the other side, I guess like the other most extreme possibility is the really big one. Let me write out S2 just as a second example. So S2 is like 14, 15, 16, 17, and then 50. So the problem is asking you to compute the average of these numbers, which means you have this like really big sum, right? It's like every S thing has like 5 things in it, and you want to find the average of all things. So basically the idea is that when you look at this, if you're going to add these up, it's much easier if you do it by column rather than by row. So for example, this is like 16 copies of the number 14. If you look at this column, there's like 8 copies of 15 and 8 copies of 41, and so on. So this guy here's up 16 times. Everything in this row shows up 8 times. Everything in this row will show up 4 times, 2 times, 1 time. Okay, however, because of the way this is set up, this row has total sum like 14 times 4. It's like 4 times the one above it. And similarly, this row here, the row after it in the tree, if you add these numbers up, like this number here is just 4 times this. This number here is like 4 times this. So this whole row will have some 14 times 4 squared. And so on. So if you actually look at what's happening, what I'm claiming is that each sum will be 4 times the previous one. So when you add these by columns on the bottom, you'll get like 14 times 16 plus 14 times 4 times 8 plus 14 times 4 squared times 4 plus 14 times 4 cubed times 2 plus 14 times 4 to the 4th. All the way on the bottom here. And you want to divide this by 16. So what you get is 1 over 16 times this is equal to 14, 1 plus 2 plus 4 plus 8 plus 16, which lo and behold is equal to everyone's least favorite number, 434, which is why this problem apparently got voted onto the test. I don't know, okay? People just really like these digits. Can't imagine why. All right, moving on. And if you know linearity of expectation, if you don't know linearity of expectation, you should read the packet and then learn the theorem, because now that you've seen this, I think it's a good time to learn the statement of the theorem. If you do know it, I mean, you should probably know how to solve the problem in that case. And if you look at the packet, it will spell out the equivalence between these two solutions. But basically what linearity of expectation does is it tells you in advance, like, it basically does this row column switching for you. Like, when you solve the problem by hand, the idea is to add the columns rather than the rows. And linearity of expectation is the theorem that does that work for you, so you don't have to invent it every time you need it. Okay, moving on. Shiba, where's my cursor? Problem 4. What the heck? Oh shit. Wrong button. I want to press the copy button. Haha. And then paste. Amazing technology. Yeah. So this probably has like this problem actually had like more computation than almost all the other problems, because you had to actually multiply like numbers together. Basically the idea is that I'll just do it this way just for educational reasons. The idea is you can think of A as a function from the set 1 to 7 to itself. And as a function, basically, it'll look something like this. Let me draw an example. Everything loops to itself. And let me put like 3 sinks. So the classification is basically that some indices I, which we'll call fixed points, have the property that like a sub I equals I. So like this is a picture where a2 equals 2, a4 equals 4, a7 equals 7. And once you decide on the set of fixed points, wow, I saw a fire somehow. I don't know. Can people put fire on this board? That's interesting. Yeah. Yeah, apparently you can put fire on the board. All right, cool. I didn't know that. Yeah, so once you decide on the set of fixed points, then for all the other numbers, so like this 1, 3, 6, 5 here, they should go to one of them. So like a1 in this picture goes to 2, and a3 in this picture goes to 4, and a5 equals a6 is goes to 7. And that's actually just a complete classification. It's like you pick the fixed points, and then everything else has to point to one of them. So in general, if there are, let's let m denote the number of fixed points, then the answer is going to be a sum across m, where there's 7 choose m ways to decide what the fixed points are. And then once you decide on the fixed points, for everything that's not a fixed point, so this is the number of not fixed. This is the number of fixed. This is to the power of m, which is also the number of fixed. So this is an example where m equals 3. So I picked like 2, 4, 7 to be the fixed points, and then for 1, 3, 6, 5, all you just pick for each of them, where do I want it to go? And then there's like 3 ways, 3 ways, 3 ways, 3 ways. So this is like 7 choose 3 times 3 to the 4th. Okay, and then that's just the answer. Like this is n. So then you have to actually compute it, which is kind of annoying. It's not too bad, but you do have to actually do it. So you just write it out. There's like 7 things. Yeah, yada yada. You get 6322. That's your answer. I don't know a way to optimize the ending computation past that, so maybe I should have picked a slightly smaller number. I think it's not that bad. But it will take a couple minutes. It's not like instant. Yeah. So yeah, this is probably the most, I think this is like the most computationally intensive problem of the 15, if you buy the textbook solutions. Okay, moving on. Problem 5. Maybe? Can I get a problem 5? Paste. Ta-da! All right, so did I mess up? M to the 7 minus m. Hang on, what did I... Is it m to... Shiba, you're right. Sorry, m to the 7 minus m. My bad. Oops. Yeah, sorry, this is not fixed and this is number fixed. Ends up not mattering because like 7 choose m is symmetric. But yeah, it is, in this notation, the not fixed points is the exponent, the choices are the fixed points. My bad. Thanks for the couch lead, coach. Okay, so Euclidean Geo. So all the length conditions A equals CD and A B equals BC basically are telling you this picture is completely symmetric. So BA equals BC means that B is the arc midpoint of arc AC, and A equals CD gives you an isosceles trapezoid. So the picture looks like this. Shit, I didn't mean to do that. Yeah, here's the picture. Ta-da! And basically the idea is like you look at this and you're like, okay, I guess we kind of use power of a point because it's, I don't know. You have the lanes that give you power of a point. So, by power of a point, 144 times 720 plus y is equal to 2x squared. Meanwhile, 864 times y is equal to 3x squared. And problem is asking for the radius of w, which will be half the diameter bx, because everything is symmetric. So, because of that, you just want to solve for y, and you look at this and you're like, oh, look, like I can just kill x right away. So 9/4 is equal to 864 times y divided by 144, 720 plus y. Okay, so linear equation, you can solve for y. Do I want to do this by... Okay, I'll just do it by hand for a dramatic effect. Boom. 3, 2... Okay, 8y, 3, 720 plus y. So y is equal to 4, 3, 2. And then so bx over 2 will then be, you add 864 to this, 1296 over 2 is equal to 648. Final answer. Yeah. And if you're the kind of person that would accidentally answer 1296, if you want to know why we picked these constants, it's so that you still got the point right, so that if you answered 1296, it wouldn't fit in the answer summation form. So, anyone who would have answered the diameter and didn't because it was over 1,000, you're welcome. Moving on. Alright, what's problem 6? Oh, the graphing problem. Alright, let me zoom out to the top here. Ah, frick, where'd it go? There you are. Do AIME. Oh my god, alright. I mean... Oh, I see, it's not done yet, so I should not stream the solutions. Okay, fine. Okay, here's the problem. So I actually was worried that this problem was too similar to problem 1, because you can actually solve this by doing basically the same thing you did in problem 1, where you're like, let n denote the floor of x. Then the equation is like nx minus n equals kx, and then you can solve for x and check whether it does lie between n and n plus 1. So the method is actually almost the same if you're in algebra, if you don't mind doing the calculation. However, then I saw the solution that was proposed by the authors, which didn't have a diagram, so I had to draw it myself. But then I saw this and I was like, oh, okay, this is actually pretty good. Which is that... Ah, crap. Come on, zoom in, zoom in. Yeah, for the record, I had to rewrite the whole solution because it was not very clearly written. But this picture helps a lot. So, what is this picture? The red is the graph of the left-hand side, floor of x times the fractional part of x, and the blue is like a random linear line. And I've labeled the intervals, so, because it has this floor function, it will always be in these waves like this, and I've labeled them I1, I2, I3, I4. Okay, so what's going on? The problem is asking, how do I pick k such that this blue line intersects the red graph exactly 24 times? And, well, if you look at each individual segment, you can actually say a lot. For example, this segment here, the slope joining this to this guy is like, 2/3. And then this one is like the larger number 3/4. So if I try to draw a blue line, for example, and I draw a blue line that hits, like, let's say it hit here, all the slopes like 5/4, 6/5 that follow are smaller. So if you hit like on I3, you will also hit I4, I5, I6, and so on. So if you want only 24 intersections, that's telling you don't touch anything to the right. Because if you hit something to the right, you're going to hit everything after it. But also, almost the same thing is true for the left, where if you hit a certain red segment like this one, there's an intersection here, because these slopes are actually bigger, like from here to the open dots, once you hit J3, you also hit J2, J1, and so on. So including the intersection at 0, which don't forget, there's x equals 0 will always work. You actually need to hit exactly J1 through J23, but not J24 or J25, etc. Okay, and then that's great. So the condition for hitting J23 is that K has to be, let me get this right. K has to be strictly smaller than 23/22. But in order to miss J24, K has to be at least 24/23. So it's literally this. Here's your condition. And yeah, this interval is 24/23 to 23/22. The length has length. Yeah, I mean, you just subtract it, right? So 1/506. And that's it. You got it. Yeah, so it's like, I don't know. I kind of have a dim view of most graphing problems because like a lot of problems that are about graphing like this are kind of there to like appease like, like random like Wisconsin state standards or whatever, where, the algebra teachers are required to have graphs. So it's very rare when I run into a problem like this where like the graph actually really makes the algebra easier, even if you decide to execute the algebra. But you don't need to, because this is actually like basically a complete proof. Like it's the only thing that you would need to expand is like when I say like you hit this interval if and only if you hit a segment if and only if you hit the top endpoint. I mean, actually, that's just true as well. So, yeah, very, very rare graphing problem for which the graph actually helps you. But if you don't like graphs, which is, my default state, I like never use this kind of stuff. Straight algebra will work too. Like follow the lines of solution to problem 1. Okay, going on. All right, divisibility problem. So yeah, ChatGPT 4 actually knew how to do this problem. I was really impressed. That was the one I was impressed by. Like ChatGPT, they are function plots, not graphs. Is there a... No, they are... Function plots are special cases of graphs, right? Oh, or unless you mean graph in like the combinatorial. Ah, okay. I don't know. Graphs like graph 3? Okay. So, I think at some point in an analysis textbook, I read the sentence like, the graph of a function f is defined as the set of points of the form x comma f of x. So because of that one sentence, I assumed the graph was actually a term and not just something that school textbooks made up. But you might be right now that you mentioned it. I've only seen it that one exercise in like Pew's textbook, where he actually was using something with it. I forget what the exercise asked to prove. It might have been something like, show that the graph is a closed subset of R squared or something like that. I have to check. But okay. Anyways. Yeah, polynomial problem. Which, yeah, I was so surprised ChatGPT could do this one. Like, I wasn't surprised ChatGPT could do problem 13 because it literally just brute forced all the n. But this one, it actually knew how to do the reduction. And let me show you what that reduction is. The idea is that x cubed is 1 mod x squared plus x plus 1. So when you do polynomial long division, what this means is that if you look at x to the 8 and you imagine doing long division on it, this is how it reduces. X to the 8 is x squared mod x squared plus x plus 1. If you don't see this trick in blue, you also would have noticed it if you had just divided, like, even if you do it the way they teach you in school, right? X squared plus x plus 1. If you actually do the division, the first thing you write down is x to the 5th, and you get, x to the 6th. You get x to the 8th plus x to the 7th plus x to the 6th, and then plus x to the 5th, and you get like x to the 7, or sorry, minus. So this is minus this, and then plus this. So, yeah, x to the 8 becomes x to the 5 after 2 steps of long division. If you are someone who's been trained on, standard school curriculum where this is how you do polynomial remainders. If you have the more highbrow algebraic, mod thing, this is also a faster way to see it, I guess. But anyways, my point is that x to the 8 leaves remainder x squared, and similarly for all the other stuff. You always just take the exponent modulo 3. So once you realize this, suddenly this problem becomes way easier, because this thing is like a8 plus a5 plus a2. Here's everything that left x squared. And then here's a7 plus a4 plus a1 times x to the 1. And here's a6 plus a3 plus a0. Okay, and if you want x squared plus x plus 1 to divide this thing, then what you find is that the divisibility condition is exactly requiring all three of these numbers to be equal. I don't need a box, I'll just write equals. So the problem is asking instead, how many ways are there to pick a0 through a8 such that these three sums are equal? And well, once you know this, because of the enormous symmetry in the problem, what you do is you're like, okay, well, let S denote the value of this sum and do casework on the number of ways to achieve a given S. So S can be anywhere from -3, -2, -1, 0, 1, 2, or 3. And then what you do is you fill in the number of ways to get it. So this is one way. -2 is I guess -1, -1, 0. Has to be that, right? And it's permutations. So this is 3 ways. -1, 1, 1, -1, 1, 0, 0. It's I don't know. This is 6 ways, I guess. And then this is 0, 0, 0, or 1, -1, 0. So this is 7. And the way you can double check that you didn't make a mistake here is that these numbers should add up to 27, which they do. So, this is the counts. And therefore, answer is the sum of the cubes of these numbers. Which is some number, freaking, how do you do? Okay, 216, 343. Okay, I can do this. I can definitely do this. All right. 2 times 2, 4, 4 plus 3, 4, 3 is equal to 821. That number sounds familiar, so I think it's right. Yeah. Proof by remembering the answer key. Wait, did I screw that up? Wait, is it 821 or 8? Shit, it's 831. Oh, fucking heck. This is how you know I'm getting old. Dude, arithmetic is really hard. I was looking at 821 and I was like, listen, something about that seems wrong. What can I say? This is what happens when you get old. Yeah, sorry, 831. Yeah, I was like, 821 looks right. And then I thought about it more and I'm like, wait, actually, I feel like that's not what it was. And then I did the last step again and I was like, God damn it. Yeah, nice 3. Yeah. All right. Problem 8. So after the test, I found out there is this thing called Commerce theorem that I probably should have heard for before, but didn't. Not that we need it. But man, where do you learn all this stuff? I don't know anywhere. Anyways, the point of this problem is basically the following: like n choose k is equal to like n minus 1, n minus 2 down to n minus k plus 1, and this is like 1, 2, up to k. And my claim is that if you want this number to be divisible by 125, then 125 on top. And basically the reason is that if you don't have any factors of 125 on the top, then when you look at the number of powers of 5, let me just give an example, all right? If I pick a random coefficient like 17 choose, I want to, let's do 37 choose 10, all right? So the number of multiples of 5 and the number of multiples of 10 will be, oh, actually I should pick a, all right, fine. Let me pick something smaller. Whatever. We only care about the 5s. There will be at most one extra multiple of 5. And the reason is that the multiple of, multiples of 5 is like, it happens every 5 numbers. And depending on where you started, you either round... I'm really getting old, huh? You either round up or down is what I'm trying to say. So if you had 37 choose 7, you only have the 35. You have 37 choose 8, you have both the 35 and the 30. But it's always like plus or minus 1 from divided by 5. And the same is true for multiples of 25. Like if I had done 27 choose 8, for example. That's probably a better example. 2, 2, 2, 2. You have like at most one extra 5 and at most one extra multiple of 25. And if that's the case, you will never have enough powers of 5. Like you can get up to like 2 extra powers of 5 using these. But if you don't have the 125s, then you're not going to get like, you're not going to get extra, you're not going to have a factor of 125 once you cancel everything out. Okay, also the same thing is true with 8 replaced by 125. So the conditions are I need a 125 on the top and an 8 on the top. So when you look at the numerator, you know that somewhere in here there's 125. Or maybe a multiple of 125, but I'm going to start my search with this smaller thing. And then you ask yourself like, okay, I also need a multiple of 8. What's the closest one nearby? And the ones closest to it are 128 or 120. So if you want both 128 and 125, you'll end up with 128. You'll end up with this thing, which is 128 choose 4. And that does, I think this one works, right? 6, yeah, there's way more. 128 has a lot of powers of 2, so it's just fine. And if you go the other way, 125 down to 120, you need at least 6 times 5 on the bottom. So this is, I don't care what this is going to be bigger. Like n plus, oh, actually, it might not be bigger. Sorry, I lied. This is 125 choose 6, right? But I think this one doesn't work because when you actually compute, let's see. So the powers of 2 here are 124, 122, 120. And on the bottom, it's 6, 4, 2. Wait, what was... Oh, no, sorry. The issue is the 5. Wait, no, hang on. Oh, shit. What am I doing? 6, 4, 2, 50. Yeah, okay. Yeah, okay. So on the bottom here, you have 2 to the 4. On the bottom, on the top, you have 2 to the 6, which isn't good enough. Okay, there we go. I thought I was going crazy there. So these are like the two viable options. This one doesn't work. This one does work. So that gives you 128 plus 4 is 132. And then obviously, if you have a 250 instead of a 125, that's way worse. Whereas here, yeah, like I say this doesn't work. Like you could also add on more numbers. Like maybe you like reach a little deeper in either direction. Like you put something in front of 125 or you put something after 120. But the issue is that this thing is already at 131. So if you increase it, you won't do better than the 132 anyways. So that's how you get this 132. I had a hard time judging the difficulty of this problem. I think the author told me that they were considering putting it at 3, like a problem 3 or 4, and I told them no. So we put it at 8 eventually. I think in hindsight, I wish I had still moved it a little up. It's kind of this ad hoc problem where you don't have to use anything fancy. Like it's kind of, you use this number if you have really good intuition for how exponents behave. Then you should be able to figure out you need the 125 and the 8, and then from there, you kind of do it. But it's not easy. It's not like just because we didn't quote any standard theory made it easy. It's just you have to. I don't know. I think this is the kind of problem that would be really, really good as an ARML tiebreaker, because all the kids who are sitting in the auditorium looking at the tiebreaker can like get started on the problem, have something to think about. Meanwhile, the people who are really, really good will get it instantly, because if you know what you're doing, there's no calculation to do, right? It's like 125, 128, 4, 132. That's it. Whereas, but also if you have 10 minutes, you stand a pretty good chance of figuring it out if you're one of the people that is in an ARML tiebreaker. So, yeah. I don't know. I don't know. I just really like this problem as like a test of like how well do you understand how exponents behave. Because you can get it quickly, but it's not standard. Those kind of problems are really rare. Okay, moving on. Problem 9. Okay, so, yeah, this problem was also kind of hard for me to place. So if you've read this certain textbook, oh shit, if you read this book in chapter 6, then you probably know pretty much what to do. If you haven't, let me show you what you're supposed to do. All right. The basic idea is that I'm gonna let the points be like 12 cosine alpha, 12 sine alpha, and then b is like the same thing with beta, beta, gamma, gamma. So I'm gonna put like Cartesian coordinates on the points. So the idea is that the centroid is the average of these. So it's like 1/3 of 12 cos alpha plus 12 cos beta plus 12 cos gamma over 3. And then the same thing with sine, which I'm going to not write because it's super annoying. And h is what happens when the orthocentric, because of the Euler line, because the origin's at 0, 0, right? So because of the Euler line, the coordinates of h are given exactly by 12 cos alpha plus 12 cos beta plus 12 cos gamma, and then the same thing with the sines. So that means that you can just kind of write down the value of OH squared because of the Pythagorean theorem. OH squared will be 144 times cos alpha plus cos beta plus cos gamma squared plus sine alpha plus sine beta plus sine gamma squared. And if you expand everything, then every time you get a cosine squared plus a sine squared by the Pythagorean theorem, you'll get a 1. So you get a 3 that corresponds to those things. And then you get a bunch of cross terms that are like 2 cos alpha, cos beta, 2 cos beta, cos gamma. I don't really care what these are, and then the same thing for the sines, yada yada. And like, even if you don't know any calculus at all, like if I ask you what is the expected value of this thing, cosine alpha times cosine beta, where alpha and beta are in 0 to pi, you should probably know what the expected value of that is, because I mean, even if you fix cosine, for each value of beta, if I just take the expectation of alpha of cosine alpha, if you have any experience with trig functions, you can probably guess what the average value of cosine is, right? And cosine alpha times cosine beta isn't any different. It's like you can either fix beta or fix alpha or do anything, but like everything is so symmetric that like the expectation of any term like this, like it has to be 0. Everything is symmetric around plus or minus. So all this is a long-winded way of saying like this dies and this dies, and therefore you get 144 times 3 is 432, and that's the answer. I heard trolley is better. Oh my gosh. Good answer. Yeah, anyways, if you do complex numbers, it's actually basically the same as this, except you don't have trig functions, and instead you're taking the average of points on the unit circle, and the centroid of the unit circle, big surprise, is 0. So, it's actually basically the same solution, but it's a little more natural, I think, if you know the complex numbers, just because you don't have to deal with trig functions. But it's not actually any different. Okay, problem 10. So this problem. Yeah, honestly, so I think I should talk about this. As everyone knows, this test was harder than an actual AIME. And the reason for that was basically at many points in the test development, I was looking at the problems I could pick from, and I was like, I can either pick the problem that I want to tell my friends about, or I can pick the problem that would be easier. And there were cases where I picked easier, but there were also times when I picked, like, even though this is slightly harder than its slot, I'll pick the problem I want to tell my friends about. And the effect of this is that I think you ended up like, I want to say this was like 2 to 3 problems harder than the actual AIME, is kind of like my spitball numbers. Like, okay, that's about as much as I'm willing to push the difficulty envelope. Probably if we do this again, which it sounds like we probably will because we had a lot of good problems that we didn't even fit on this test. I will probably just say on the outset, we think this test will be about 2 to 3 problems harder than the real AIME. Deal with it. But yeah, this test was harder than normal, and it's because I wanted to. There were certain problems I couldn't bring myself to cut them, which shame on me, I guess. But yeah, here we are. Yeah, Euler line on problem 9 is kind of it's a little pushing it. I don't know if the actual AIME would be willing to do that. How often does Evan check the queue? Basically, it depends on how busy I am. Like, I check the queue when I have a moment to breathe between whatever else I'm running around doing, which honestly, for the most part, is just lying in bed. Uh, but last week was just really, really bad because I had mystery hunt, so I was kind of just doing puzzles 24/7 for like. Sorry, that's a lie. I was doing a combination of puzzles and sleeping 24/7 for like 3 days. And then I got back and the queue had like 70 submissions in it, and I was just like, but we got it down back to 0, and I hope my advisor isn't too mad at me. Okay, moving on. Problem 10. So this problem is Here, let me show you something, alright? This is a multiple of C because it's the LCM. This is also a multiple of C. So therefore, C, in any solution, C has to divide the GCD of A and B. And if that's the case, then it follows that if C divides A and B, then this number is actually just B, and this number is just A. So actually, this equation can be simplified to just GCD AB plus B equals A cubed. Yeah, so B is equal to like A cubed minus something that divides A and B. So this is basically a complete description of the solutions. It's like you pick A, and then you pick like a divisor, and then that's just it. So in particular, the set of valid B's are like, so B can be like 2 cubed minus anything that's either 1 or 2. B could be 3 cubed minus 1 or 3. Or like when you get to 4, it's like 1, 2, or 4. And when you get to 10, it's like just a set of divisors, 1, 2, 5, 10. Or the possible values you can have. So the answer is you sum from A equals 2 to 10 of, I always get the notation wrong. Is it tau? We'll just say number of divisors, all right? Okay, so that means for the numbers from 2 to 10, I need to count how many divisors they have, which I really hope I can do correctly. We'll find out. Prime, 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 prime. Oh my god. Let's try that again. Prime, 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 prime. Square of prime, square of prime. Semi-prime, semi-prime. Cube of prime. I think that's right now. So this gives 26, I think, when you add these numbers up. Nobody saw that. Oh my god, primes have one divisor. Jesus Christ. Okay, moving on. Nobody saw that. Alright, let's go back up to the top. Problem 11. Apparently one of the least solved... Yeah, this problem was way harder than I expected it to be. So... yeah. I think what I've learned from this problem is that anytime you have edge cases, it kills people. Because I think the thing about this is, like, if you want to brute force the problem, okay, like, what you do is you write, like what most people did when they saw this problem is, like, okay, arcsine, let me just let x equals root n, okay? Equals 120 degrees minus arcsine b over x. And then if you take sine of both sides, you'll get some sort of equation. And then, like, you know, you bash your head against it and then stuff happens. Is Pretzel bugging? I don't think so. Let me check my audio. Oh my god, it hasn't been playing. Oh my god. No! I'm sorry, I forgot to change the audio into desktop. Shiba. I'm sorry, I've been sitting here listening to music the whole time. Oh, apparently it didn't show up in the stream. Oh my god. Oh. Now I'm upset. I don't think I have the patience to like manually insert music into the video later when I upload this to YouTube, but I'm so upset right now. Oh my god. God damn. That's the problem with streaming, is like if you fuck up, it's so hard to go back and fix it. Okay, whatever. Anyways. Sorry, what was I saying? This is a one-way implication. So, I feel like, I don't know, if I was doing this, like, this would give me the heebie-jeebies, because I'm, like, taking the sign of both sides. It doesn't go backwards, right? Like, a solution to this second equation I have written down here, will not necessarily give you a solution to the original. And I think that's something that apparently people don't get burned up by enough, because, I mean, a lot of people were staring at this wondering why the answer was bigger than 1,000. Again, I made it bigger than 1,000 so that you would know if you missed something. You're welcome. But they actually even couldn't fix it. So, yeah. If you're one of the people that was staring at this wondering why the answer wasn't 1,200, this is something I think you need to pay more attention to. When you do steps like this, they're not reversible. It is not true that any solution to the second equation will give you a solution to the first equation. So, yeah, if you were trying to answer 1,200, please pay attention to things like this. It doesn't burn you that often, but it will burn you, and this is an example of how. Anyways, okay. This is not what we're going to do because it's super annoying. We're just going to do the geo solution instead. So, actually, before I even get to the geo, I want to ask, like, when is there any solution to arcsine a over x plus arcsine b over x equals 120 degrees, where x is at least the max of AB. If x is smaller than this, then the arcsine isn't even defined, so it's, you know, a problem. And the answer is that this left-hand side is decreasing in x, and this, it's a decreasing function of x. When x is here, it's like arcsine a over b plus arcsine. Sorry. Oh, this is super annoying. Okay, can I just assume a is at least b without loss of generality? That'll probably make this easier to write. So I'm just gonna write this. Okay, so x is equal to a. Yeah, cool. So this is arcsine of 1, arcsine b of a. And as x goes to infinity, the left-hand side goes to 0. So if this is 90 degrees. So in order for there to be a solution, you need the biggest value of the left-hand side to be 120 degrees, i.e. you need arcsine of b over a to be at least 30 degrees, which I think should just be the same as b being at least 2a. So because of this, and because of this, the conclusion is that when b is at least 2a, and a is at least b, there is one solution. Exactly one solution, and otherwise 0 solutions. So this is the part that messed a lot of people up, which is that if you do irreversible steps and you don't pay attention, you know, you'll get some solutions in x that don't actually fit the original equation. Like, this happens sometimes when you like square both sides of an equation that has square roots, but it really happens with inverse trig functions. Like, inverse trig functions give me the heebie-jeebies exactly because they're so hard to reverse. And in this case, we're lucky that the left-hand side is monotonic in x, so, you know, it kind of works out. But yeah. Okay, I think I said like be careful like 10 million times now, so let's just move on. So anyways, we'll just remember this for now, and then now let's figure out what the solution is. So if there is a solution at all, here's what I'm going to do. I'm going to construct a circle with diameter x, and we're going to let this be b, this be a. These are right angles because it's a diameter, so this is 120 degrees. Okay, so by the law of cosines, this thing here is a squared minus ab plus b squared, square rooted. By the law of sines, because we're in a circle with diameter x and the angle cut out is 120 degrees, this will be like root 3 over 2x. So x is exactly given by 2 over root 3 times root a squared minus ab plus b squared. So when a solution exists, it corresponds to this value of x. And n, which is x squared, will be 4/3 a squared minus ab plus b squared. I don't know, like, I feel like I'm surprised people didn't know you could do this already, because I feel like adding 2 arcsines is like, it's not very artificial of a setup. Like, you should be able to add 2 arcsines. Anyways, with that in mind, the TLDR is that we're trying to count the number of solutions to a squared minus ab plus b squared being a multiple of 3, and either, well, we'll just say a less than b and b less than or equal to 2a are the boundary conditions. Earlier I assumed without loss of generality that a is at least b. Once you drop that constraint, this is what you're counting. And you can just count it by brute force. In particular, one way you can make this a little easier on yourself is that a squared minus ab plus b squared is like a plus b squared minus 3ab. So actually you just want this to be 3 divides a plus b. So, you know, a and b are between 0 and 60, you want their sum to be divisible by 3, and you want them to lie in between this region. And if you brute force, you know, just do the cases, it's not that bad. It takes like 5 minutes, you'll get it eventually. However, it was later pointed out to me that there is a way to bypass the annoying part of the problem if you are really good at reparametrizing stuff. And that solution goes like this. What we're going to do is we're going to set a to be equal to... So it turns out that the conditions are equivalent to this. You can set a and b to be, because of the divisibility by 3, and because of the a less than 2b, b that most 2a, there exists x and y, non-negative integers, and not both 0, such that a is x plus 2y and b equals 2x plus y. In fact, you can explicitly solve if you really wanted to. X is like 2a minus b over 3. B is like, y is like 2b minus a over 3. So actually, you want to count x pairs x and y such that this thing is at most 60, and this thing is at most 60. So that corresponds to counting lattice points in the following region. So here's a picture of an xy plot. This edge corresponds to, I'm gonna get this wrong. A, did I say A is x plus 2y? This, okay, so this was the b less than 60 line. This is the a less than or equal to 60 line. This guy, this guy. So you want to count how many lattice points are in here. And there's a tool that lets you count lattice points in polygons. It's called Pick's theorem, where I plus b over 2 minus 1 is equal to the area of this blue quadrilateral, which is apparently, it's 400 plus 100 plus 100, 600. And the number of boundary points, so there's like, it's like, you go along the perimeter, right? And you get like 60 plus, sorry, not 60, 30. Well, Yeah, so you have to be a little careful about fence post errors, but it's like for every segment it has both boundary points. So it works out in the nice way where it's like you count this guy and not this guy when you're counting this thing, and then you count this guy and not this guy. Anyways, number of boundary points is 80, so the number of interior points by Pick's theorem becomes exactly 561. And so answer I plus b and then minus 1 because we want to throw out 0, 0. Is equal to 640. So yeah, bit of black magic. Because you know there's actually no computation. It's just this thing. I don't think this is what I was expecting people to do. I was expecting people to like reach this point and then just be like, okay, you know, it's a little annoying, but you should be able to do it, and then you just kind of run it over. Okay, going on. Haha, rubber bands. Yeah, so this problem also ended. Oh, what the heck? That's not what I wanted to do. This problem also ended up being way harder than I thought it would be. Yeah. So, I don't know. I thought this problem would be doable because I looked at it and I like knew how to solve the problem before I finished reading what it was asking for. Because the basic idea behind the problem is that when you want to count rubber band configurations, all you have to do is zoom in on a peg. This is what the picture in the official solution packet looks like. And the configuration at the peg uniquely determines the entire picture. So, yeah, it's kind of like... yeah, that's literally the whole thing. So, you look at each peg and you ask how many things are sticking out of it and how many ways are there to configure it. And you get this picture. So the blue number is how many edges are sticking out of it. The red number is how many ways there are to match them. So you take everything in the red picture and multiply it together, and it gives you n is 15 cubed times 3 to the 9th, which you can see already is a multiple of 125, and if you work out mod 8, this is minus 1 cubed times, well, yeah, just 3. So this is like 5 mod 8, I guess. And also 0 mod 125. So you put these two together, and the answer is 125 mod 1000. That's it. That's actually the whole solution. So yeah. Thank you, Nadia, for the follow. Alright, going on. Problem 13. Yeah. Dude, I'm still so upset the audio is muted on... That means like all the soundboard sounds didn't come in either. Like, oh, my entertainment. Okay, so first, what I think the main thing I should communicate is that notice that because all the exponents are even, like anytime n works, so does 2024 minus n. So the average of all working n will be exactly 1012. And therefore, all I need to do is tell you how many valid n there are, rather than just, what the heck? What did I do to my scaling? Yeah, so the average will be 1012, and I need to just compute how many of them work. So, because, first of all, okay, I have to factor the year first, right? 2 cubed times 11 times 23. So, let's just look modulo each of these things. Well, okay, the other thing I want to do is set up the Venn diagram. So, this is n to the 22 minus 1, this is n to the 40 minus 1. The overlap is n squared minus 1, because the GCD of n to the 22 minus 1, n to the 40 minus 1, is n to the GCD 22, comma 40 minus 1 equals n squared minus 1. So I'm just going to make like this chart here, where this is mod 8, mod 11, mod 23, and say how many solutions are there to n to the 22 is 1, mod that thing, n to the 40 is 1, and n squared is 1. Okay, so the bottom row is most easy to fill in, because mod 8, this is all the odd numbers, this is plus minus 1 mod 11, this is plus minus 1 mod 23. There's some other entries that are pretty easy to fill in, like this one is also just everything odd, everything odd. Mod 11, n to the 22 turns out to be n squared is 1. So this is actually also 2. It's just the plus minus 1 mod 11. And by Fermat's little theorem, this one will be 10 solutions. It's everything that's not 0. Similarly, this thing here, this is 22. This is everything that's not 0. So the only one that's like a little annoying to compute if you don't know your theory is how many solutions are there to n to the 40 mod 23. And I think it turns out to be 2 plus minus 1 as well. And if you know primitive roots, how primitive roots work, then that's probably the easiest way to see it, honestly. If you know primitive roots, you look at the GCD of 40 and 22, it's 2, so you need n squared to be 1. If you don't know primitive roots and you want to hit it with a hammer, I guess the easiest way to see it is that if n to the 40 is 1, also modulo 23, n to the 22 should be 1 as well. So these two together should imply n squared is 1. So same thing. Okay, so because of that, this lets you compute all the numbers in the Venn diagram. By the Chinese remainder theorem, this one is equal to, I mean, it's the product of the numbers, right? And then this one is 4 times 10 times 2, and this is 4 times 2 times 2. Okay, so now you have to be a little careful because when you have this Venn diagram, you're trying to count the number of things that are outside. So the answer is going to be this number plus this number minus twice this number, because you're actually excluding the thing in the overlap, not just deleting the overcount. So yeah, a lot of you might forget this 2x. I think I forgot it too when I was doing the problem the first time, but you know, that's life. Anyways, compute this number. It works out to heck. Okay, so 4 times 44 plus 20 minus 16 is equal to 192, right? Maybe? I hope? Pray? No, I think that's wrong. Sorry, this is... I'm just making an idiot of myself on stream. 56? So this is 224. Okay, and then finally, final answer comes out to 224 times 1012, which is 688 mod 1000. Okay, that's it. Okay, almost there. 2 more problems. So, problem 14 is this thingy. This is one of the longest problems on the test, I think. Like, there's a lot of ways you can set it up, some of which are uglier than others, but even the optimal setup takes a little bit of time to execute. So, alright. Obviously, you're going to have to label some lengths, so let's label some lengths. I'm going to call them A, B, C, D, E. Here's the picture corresponding to that. I'm just going to have this on top of the diagram in the original picture because you don't need the original once you have this. Yeah, red win the otter. Okay, so as is typical for geometry, you have a bunch of variables, you have a bunch of equations. And so because I have 5 variables, I want to get at least 5 equations. And let me write down 5 equations. So the obvious ones are that b minus c is equal to 2, d minus a is equal to 3. At least if you look at the picture, it is technically true that it's possible that these two numbers swap. You don't actually know which one is which, like, obviously. But when I write the later equations, I will point out where it becomes obvious it has to be this order and not the other one. Okay, moving on. The next equation I'm going to write down is the area equation. So one of the triangles had an area of root 3 over 2 times, sorry, root 3 over 4 times a plus b plus e all squared. The other one, root 3 over 4, c plus d plus e all squared. And then the area of the whole, which, if you don't know how to compute the whole's area, let me show you how it goes. 3 to complete this to a triangle. So the whole is like the root 3 over 4 times 7 squared, so the area of this whole triangle here, minus 3 times the area of the little one inside it. So anyways, yeah, you will get, I think the area of the whole works out to 37. So if you cancel out all the root 3 over 3 over 4s that are everywhere, here's your third equation. Here's equation number 3. Okay, so I promised I need 5 equations, right? So far this is 3 equations. So the sort of naive thing to do is try to use the law of cosines because of the 60-degree angle. It turns out you don't have to do this. And the way you can get the last equation, because I promised you there's a solution, well, I didn't say this, but there's a solution not using trig at all, which is the one I'm showing. And it wrenches on this pair of similar triangles. In the blue, it's CDE. In the yellow, it's E plus A, B plus E, C plus D. Let me make that a little clearer. So that's actually 2 more equations, and that's good enough. We will not need to use the law of sines or the law of cosines. This equation says C to D to E is in the ratio A plus E to B plus E to C plus D. So ta-da! 3 equations. Sorry, did I say 3? I meant 5. Yeah, so now that we have the equations, we're trying to compute C plus D, and we just need to solve these things for the resulting variables. So let's do that. The really big brain thing that you can do at this point is, in this equation, rather than this ratio, I'm going to change the left-hand side to something else, which is what you get when I add pairwise the things. So this A plus E is like this thing plus this thing, and then similarly for the others. So when you add ratios like this, the ratio doesn't change. And what that lets me do is that if I define this sum here, c plus d plus e, shiba, to equal s, then this right-hand side is equal to... Okay, so c, d, e will be our base variables. I'm going to kill off every time b and a appears. So this one will be s plus 2. Sorry, a is d minus 3. It's s minus 3, s plus 2 to s. So actually when I do this, when I write this out, CDE is equal to this ratio of the sums. You can actually just solve at this point for s, right? Because like... if I normalize... I think this is correct, right? So you actually just know everything at this point. You can solve for s directly. I forget exactly what it is. Hang on, so I screwed something up. It should be a plus sign, but... C to... No, hang on. I'm being a stupid head. Ignore everything I just said. Sorry, this doesn't give you the sum. What am I talking about? Never mind. Plan B. We have one more equation, right? We can get the sum out of that. Because this equation here says... Because like this left-hand side is just s squared. And then a plus b plus e is like... s minus 1, I think. Yeah, this is s minus 1. So this solves to give you the value of s, which will be... Sorry, this is 37. So s is 19. That gives you this ratio. This is now 16 to 21 to 19. And if we know the sum and all the ratios, that should let us recover CDE. Namely, C equals 16 over 56 times 19. D equals 21 over 56 times 19. And E is just whatever it is. We don't care what E is because the problem is asking for C plus D. C plus D is equal to 19 times 37 over 56. So this is 703 over 56. And that gives you the final answer, 759. Yeah, I think you're right. It's over 3s minus 1. I was being stupid. Ignore that brain fart. It's easier to get s out of this equation anyways. This equation I think you should have been able to get. Well, actually, maybe that's not true. You should be able to get s out of that equation, right? No, that's not true. If you could get s, you could get CDE. Okay, so I'm just being stupid. Never mind. Yeah, but anyways, you can get s from here, so everything's okay. All right. Okay, last problem. Conic geo. What the heck? Why does that show up? The heck? Why can't I copy paste this picture? There you go. Okay. Okay, so, I think what I learned from this problem is people know a lot of fancy stuff about parabolas that no one ever told me. Like, I don't know. Do people actually know conic stuff? Because I sure don't. Anyways, the intended solution was just this, okay? conics have this shape. You know, there's some general equation like this. And when is an equation a parabola? It's a parabola if it passes, if this part is a perfect square, is the theorem. It's like ax squared plus bxy plus cy squared is a square. One way you can think about this is that a parabola passes through exactly one point at infinity. And the points at infinity, how do I say this? If you know your fancy projective stuff, which I guess I kind of know a little bit, points at infinity correspond to z equals 0. So you want exactly one solution when I put this phantom z in, it's 0. Basically, like, points at infinity are when x and y, only the ratio of x and y matter, and then the lower order dx, ey, f drop out. So if you want exactly one of them, that red underlined part had better be a perfect square. Okay, so that's the condition for a parabola. Now, what does it mean to be tangent at 1, 0 to the x-axis? Well, if you're looking at the x-axis, that's the set of points for which y is equal to 0. So what that's saying is that ax squared plus dx plus f is supposed to be some constant multiple of x minus 1 squared. And finally, what does it mean to be tangent at 3, 0, or sorry, 0, 3? Similar thing, except I throw away everything that has a x in it. So you set x equals 0, and you want cy squared times e plus ey plus f to be some constant multiple of y minus 3 squared. So, like, I don't know, like, here's your relations. This uniquely determines the entire equation of the conic. So by scaling, let's assume, if by scaling I assume f equals 9, then what happens? Then this thing better be exactly y minus 3 squared. And this thing had better be exactly 9x minus 1 squared. So which coefficients do we have? F is 9. C is minus 6. Sorry, that's just minus 6y. Wait, no. Sorry. C is y plus 1. And then you fill in minus 6y. And then minus 18x. And then the x squared coefficient is 9. Okay, so the only one that I don't have yet is the xy. But I want ax squared plus bx plus y, cy squared to be a perfect square. So I think here, do I put... Actually, do I... Okay, I guess this branches into two cases. This is either plus or minus 6. We don't know which one yet. But, yeah. The result of 4 quadrillion times 4 times quadrillion is 16 quintillion. Is that true? That doesn't sound true. I think you need to replace quintillion with something bigger. Okay, where was I? So, these are two equations. One of them is actually extraneous because there's a... So, in the... plus case. In the plus case, this is actually equal to 3x plus y minus 3 all squared. So it's actually a really thick line, which is not what you want. So we're actually in the minus case, and so it comes down to like, okay, how do I find the vertex of a parabola now that I know what the equation is? And what you want to do is you want to transform the coordinates. So this is actually how you would have found the first one to begin with. I should have started with this case, honestly. It's a little easier to see what's going on. But you start by taking the square term, that's one thing. Okay? And then once you have the square term, the other one I want to write everything in terms of this coordinate and the rotated coordinate, which is x plus 3y. So that's kind of this rotated thing. So I want coefficients to put here and here and plus 9. So the basic strategy for finding the vertex is that I'm going to change to new coordinates. We'll call them like capital X and capital Y, such that the thing that I get will be y equals x squared plus constant x plus constant. And the reason for picking this one is so that the new coordinate system is still orthogonal. So it's just like axis rotation plus homothency. Okay, so now that's a linear algebra problem, and you solve the coefficients, you get... crap. I have to... Okay, let's see. 3 times something plus something is 18. I'm just gonna go. Sorry, also, you don't know this is 9. This could be any number. Just doesn't matter what that constant is. Okay, so if I believe this, then... Hang on. Something's off. I flipped the sign somewhere. This should be minus u. Okay, cool. How do I solve systems equations? Echo, stop! Don't need your help. Let's multiply this by 3, subtract this. 10u is equal to 54. Okay, so this one will be... Thank you, Trevor, for the follow. Okay, so this one is equal to 24 fifths. This one is equal to 18 fifths. And then constant... Well, actually the constant is 9 because this part doesn't touch the constant at all. So the rotated equation is x squared yeah, so rotated equation is whatever it is. X squared minus 2... I'm gonna mess this up. It's like x minus 12 fifths squared. This y has like an 18 fifths in front of it. And I guess this is like, I don't know, whatever the heck it is. We don't really care, because the point of writing it this way is that when you have a parabola in... Does bro have a Discord? Oh, yeah, let me link my Discord. Yeah, the point of writing it this way is that when I write a parabola in the form y equals something squared with only x, we actually know just how to find the vertex of it, because that's standard. So x is like 12 fifths plus whatever the heck it is for y. I don't really want to back solve. I guess I might have to actually back solve the... Okay, fine, I'll compute the thing. Okay, so I wanted to subtract 144 over 25 from 9. 81. So the number I need to put here is 144 over 25, 9 minus that. So this is like 81 over 25. Okay, and then 5, 5, 2, 10, 9/10, I think. Okay, so this is the vertex in the rotated coordinates. And then now I have to put this back and solve for the normal coordinates. Okay, so solve. Oh, nice. So multiply this by 3, I guess. And add. Sorry, wrong one. I want to multiply the other one by 3. So 10x equals 36 fifths plus 9/10. 1072, 8110. So x is equal to 81 over 100. Meanwhile, y should be equal to 3x minus 12 fifths, which is 243, 3 over 100. I guess. Okay, and then 81 plus 3 over 100 is 21 over 25. So final answer is 046, and we're done. There's a conics hand that I should read. I don't know this conics stuff off my head, okay? Like I don't know. Okay. Thank you, Catlo, for 1 bit. Okay, so man, I'm still really mad that there was no music or sound effects for the first hour and I didn't realize. I have half a mind to like redo the first hour so I can like get the sound effects in, but that's probably not a good use of time. Damn it. This is what happens when you don't stream regularly enough. It's just every time you forget one part of the setup. And it's okay. Anyways, that is all 15 problems. If you want to know why I never got a 15 on the AIME, watching this stream probably informed you why, because I cannot for the life of me do simple tasks like find the number of divisors of a prime correctly. Go to the Discord and see what I sent you. Lol, okay, I mean. Product of 4 quadrillion times 4 quadrillion is 16 quintillion. Thank you, ChatGPT. That was very enlightening. Anyways, yeah, we're done.